Okay, very good morning, one and all. So in the last class, we discussed regarding the delta modulation transmitter section, receiving section, and its SNR calculation. Okay. So what is the importance of opting delta modulation? Even we have a PCM technique. The main advantage is that delta modulation can reduce the channel bandwidth because we have redundancy problem in the case of PCM. Okay, that we can overcome using the delta modulation. In delta modulation, it transmits only 1 bit per sample. Only 1 bit per sample will be transmitted. Okay, so because of that, we can say that the channel bandwidth, the requirement of channel bandwidth in delta modulation is very less compared to that of PCM. Okay, so but what are the drawbacks we studied? We studied that our delta modulation cannot be capable of handling two types of signals, two kinds of variations in the amplitudes of message signal. What are those two kinds? When the slope of magnitude of m of x of t is very high, okay, then one kind of error will arise so that our staircase waveform cannot approximate x of t. Okay, that problem is called a slope overload error. And second drawback is when the magnitude of x of t is very constant, is very flat. Okay, if there are no like minute variations in message signal magnitude, then we'll have second type of error that is called as granular noise. These two kinds of drawbacks are mainly due to the fixed step size that we take while transmitting the signal using delta modulation system. Okay, so what are the drawbacks? So slope overload distortion and granular noise, that is mainly due to the fixed step size. Now in order to overcome the drawback, we need to vary the step size in accordance with the amplitude of message signal or the input signal. Okay, input signal is nothing but the message signal. So we need to consider the magnitude of x of t, and based on the magnitude of x of t, the step size should be accordingly varied. Okay, you should vary accordingly. You should vary the step size in accordance with the magnitude variation of x of t. If the magnitude of x of t suddenly increases, or if there is any abrupt increase, so that if the slope of x of t is very high, that may be in the increasing manner or in the decreased manner. Okay, so like that, based on the magnitude of x of t, okay, so accordingly the step size should be adjusted. Okay, so we can discuss in clear if you go through the adaptive delta modulation. So what is the advantage of adaptive delta modulation? So because we have slope overload distortion and granular noise, in the case, these are the two main drawbacks of delta modulation. Our delta modulation SNR will reduce. So in order to improve the SNR of delta modulation by making the step size as adaptive or variable, okay, you can increase the SNR by varying the step size. Okay, so that is the main advantage of adaptive delta modulation over delta modulation. So because the SNR of delta modulation is very poor due to the occurrence of two kinds of errors, namely slope overload distortion and granular noise. You can opt adaptive delta modulation so that these errors we can reduce, so that we can improve the SNR. Okay, now let us move to the next slide. In this, we will discuss in detail about the adaptive delta modulation advantages over delta modulation. And second thing is, you can see the transmitter and receiver sections of adaptive delta modulation. Okay, so now what is the main drawback of linear delta modulation? In linear delta modulation, step size will increase. Okay, step size will increase. But what is the main drawback? In adaptive delta modulation, the step size is almost a constant value. We need to increase the value of step size. Of ADM. Okay, step size of the staircase waveform generally you can consider adaptive delta modulation. Please all of you observe the first point. In the first point, if you observe, what is the first drawback? Linear delta modulation will provide constant step size. This constant step size will introduce two kinds of errors in the traditional or linear delta modulation. Okay, so that's why SNR of linear delta modulation is very poor. So in order to overcome those two quantization errors, namely slope overload distortion and granular noise, step size should be made adaptive. How it should vary? It should vary in accordance to the variations of magnitude of x of t, magnitude of input signal. Okay, for example, ADM, this adaptive delta modulation, what it will do? It will increase the step size for steep amplitude variations of x of t, and it will decrease the step size for minute amplitude variations of x of t. So based on the amplitude variations of x of t, accordingly, this adaptive delta modulation will vary the step size. Okay, so if the slope of x of t is very high, then ADM will increase the step size. If the slope is almost all flat, like 0, nearer to 0 or lower value, then it will reduce the step size. This is the logic used in adaptive delta modulation. Other than this logic, the transmitter and receiving circuits of adaptive delta modulation is similar to that of linear delta modulation. Okay, so because the step size is made variable or made adaptive, this linear delta modulation, because here we are calling this step size as adaptive, so we can call this delta modulation as adaptive delta modulation. Okay, and you can also, so many possibilities, like this adaptive modulator can be able to take continuous change in step size or discrete changes in the step size. Okay, this can introduce either continuous change in step size or discrete change in the step size. And how it can provide this kind of continuous change or discrete change? By making use of one logic introduced in the circuit. Okay, by making use of a logic introduced in the circuit, in order to vary the step size, you can develop continuous change in the step size or discrete changes in the step size. Let us see the transmitter and receiving circuits of adaptive delta modulation. Please observe the circuit of transmitter circuit. So the first figure shows the transmitter circuit of adaptive delta modulation, and second figure shows the receiving section of adaptive delta modulation. Now, any one of you, can you respond and tell me what is the additional block used here other than the delta modulation circuit? Can any one of you specify what is the extra block added here? What is the extra block added here other than the traditional delta modulation circuit? Any one of you? In the last class, we discussed the delta modulation transmitter and receiving circuits. Okay, so what is the additional block added here in order to vary the step size? Can any one of you respond? Please observe the circuit of this ADM transmitter. Here input x of t is once again compared with the x cap of t, where x cap of t is a past sample. That past sample value is stored in the accumulator. What is accumulator? Accumulator stores the staircase waveform. Okay, this is mainly used to store the past sample information. Okay, so in delta modulation we use the accumulator, and here also we are using the same accumulator. And in delta modulation, only one bit is transmitted per sample. Okay, so the same thing we used in delta modulation. Okay, and what else? What is the additional block added here? What is the additional block added here? Can any one of you tell me?
Logic step size control.
Yes, only one additional block added here in the case of adaptive delta modulation when compared to the traditional DM circuit is logic for step size control. Other than this circuit as well as the equations, everything or the expressions for the output, everything is almost all same, except we are using certain logic in order to control the step size. Okay, how you should control? So whenever the x of t magnitude is very high, then our step size you should increase a lot. Okay, for example, if we have no amplitude variations in x of t, then we should reduce the step size magnitude. So what this 1-bit quantizer do? 1-bit quantizer will generate a staircase waveform which is B of NTS. So what is the output of 1-bit quantizer? Same as that of in DM. In DM we use it with the same variable, that is B of NTS. Okay, so 1-bit quantizer develops a staircase waveform. First it will generate the output with a variation of plus or minus delta. Okay, so in the case of traditional DM, and in the case of DM it is equals to delta into sine of E of NTS. Here error E of NTS is positive when the present sample, that is x, is greater than x cap. When x is greater than x cap, error is positive. Okay, so this 1-bit quantizer increases the output magnitude. Okay, when the error is negative, when error can be negative, when the comparator difference, that is when the present sample data x is less than x cap, past sample data, then error will be negative. When error is negative, this 1-bit quantizer, it keeps in mind that we have to reduce the step size for staircase waveform. For the existing staircase waveform, we should reduce the step size. Up to that, the principle is same as that of traditional linear delta modulation. But here what we will do, the output of 1-bit quantizer is fed back to the logic, okay, one circuitry, so that it will control the step size. What we'll do there, we'll write some logic. Okay, so that logic should be such a way that our staircase waveform magnitude should be very high for higher magnitude variations of x of t, and for low magnitude variations of x of t, step size should reduce. Okay, so like that a logic should be written here. Now once again the 1-bit quantizer output is fed to the accumulator, the feedback section, so that this accumulator data is U of NTS, where U of NTS is a staircase waveform. Okay, so U of NTS is the staircase waveform which is stored in the accumulator. Now the amplitude variations of U of NTS can be provided by B of NTS, where B of NTS is the output of 1-bit quantizer. And please always remember here that here delta is the variable step size. Okay, so other than this logic used for step size control, almost all the principle behind adaptive delta modulation is almost all same as that of our traditional linear delta modulation. Okay, now please observe the ADM receiving section. Please observe ADM receiving section. If you observe the adaptive delta modulation receiving section, what is the difference between DM receiver and ADM receiver? Here also we are using the additional block, that is logic for step size control in the receiving section. Other than this logic, the accumulator section followed by low pass filter, that is the traditional linear delta modulation receiver section. Okay, so the only thing that you should remember is that here there is almost all the circuit, that is for both the transmitter section and receiving section, circuit is almost all same as that of linear delta modulation. So here we are using some logic to control the step size, because we need to avoid the quantization errors. What are the two errors that arise in the case of delta modulation? Slope overload distortion and granular noise. We need to control the two errors in order to improve the SNR. Okay, so a logic for step size control is used in the case of ADM transmitter and ADM receiver. Okay, so the main agenda is to improve the SNR by reducing the slope overload distortion and granular noise. Okay, that arise in the case of linear delta modulation. So you can see the working principle in the case of in the next slide. Okay, so the only difference between, please observe the first point, the only difference between the DM and ADM transmitter and receiver circuits is the addition of a new block, namely logic for step size control. This is added in ADM, both transmitter as well as receiving section, and the step size is made adaptive. Okay, and it's made adaptive or variable according to the logic used in the 1-bit quantizer. According to the logic, and that logic depends on the output of 1-bit quantizer. We represented the output of 1-bit quantizer as B of NTS. For example, so this is one of the example of logic. So like this, you can introduce like varieties of logic, and so that our SNR, so ultimate thing is you need to improve the SNR value. So ultimate thing is you need to increase the SNR by reducing the two errors developed in linear delta modulation. So this is one of the examples shown here, logic. So if the 1-bit quantizer output, that is B of NTS, is 1, then step size can be doubled for the next sample. This is the general one used. Okay, so general logic for step size control is if the 1-bit quantizer output, that is B of NTS, is 1, then step size will be doubled for the next sample. Okay, for example, if the B of NTS, that is output of 1-bit quantizer, is 0, that is low, then you can reduce the step size by 1 step. Okay, like this we can make use of different logics, but this is the general used. This is the general usage of. So this is the generally used logic in adaptive delta modulation. Okay, if 1-bit quantizer output is 1, it will increase the logic is added such that step size should double. And if the 1-bit quantizer output B of NTS is 0, step size you should made it reduce. Okay, now so similarly the same 1-bit logic control, the same thing is used at the receiver. Okay, and the same principle you should use here at the receiving section. So you have used some logic at the transmitter section. Okay, so the same logic you should implement at the receiving section so that you can recover the X of t at the output properly. Okay, so now this what this logic control will do. So at the receiver, the logic control generates the step size based on the incoming bit. Okay, so based on the input to the receiving section, what this 1-bit quantizer will do, what this logic for step size control circuit will do, it will once again compare the present sample data with the past sample data, present sample data with past sample data, and after comparison, it will increase or decrease the step size. Okay, and the logic used at the receiver should be same as that of the logic used at the transmitter section. Now the variable step size, okay, is applied to the accumulator. We know the importance of accumulator. So the same accumulator used at the transmitter will be used here. Okay, so the accumulator, we know that accumulator generates the staircase waveform by storing the past sample information. Okay, so then the low pass filter, then the data obtained from the accumulator is fed to the low pass filter. Okay, what this low pass filter do? This low pass filter smoothens the staircase waveform. This low pass filter smoothens the staircase waveform to reconstruct the, in order to reconstruct the original form of X of t. Okay, this is the operating principle of adaptive delta modulation. and we have seen the transmitter and receiving circuits. Okay, so the everything other than the logic for step size control, the circuit of delta modulation is similar to that of, the circuit of adaptive delta modulation is same as that of DM circuit or linear DM circuit, except the another circuit used added from the output of 1-bit quantizer to once again the input, that is called as logic for step size control. It is added both in the transmitter section and ADM receiver section. Okay, now you can see the waveform here. So what is the input to the DM transmitter? Input is X of t. What is the output generated from the ADM adaptive delta modulator? That is staircase waveform U of t, because our like transmitter section, what it will do, it has accumulator. Accumulator always stores the U of t. Okay, accumulator stores the staircase waveform. Please observe the graph here. So here message signal magnitude, slope, message signal magnitude, or you can say the amplitude variation of X of t is very high, or you can say that slope of X of t is very high. Then what is the logic used in ADM? So based on the logic used on ADM, what it will have, the step size is doubled to that of earlier sample. Step size is doubled to the earlier step size, past sample. And like that, whenever we have like lot of difference between the present sample and the past sample, then step size is doubled. Okay, if there is lot of difference, like minute difference between the present sample and past sample, then X of t is reduced by 1 step. That is nothing but you are making the step size to half that of the original magnitude when we have flat X of t. See, initially we have the slope of X of t is very high. At that time, what we are doing, the logic should be such a way that the step size for the staircase waveform should double. Okay, later once again X of t rapidly reduces. Okay, then also X of t step size of U of t should double. Now later after some time, what happens to X of t? There are no amplitude variations in X of t, or we can say that like slow amplitude variations. Then what we are doing, the step size is reduced to half. Please observe here. Please observe the step size of staircase waveform when X of t variations are very minute. When X of t amplitude variations are minute, then what we are doing to step size, the logic has written in such a way that the step size is reduced to half. So please clearly observe the step size variations of U of t. The step size is doubled when present sample magnitude of X of t is far greater than the past sample magnitude of X of t. When the present sample magnitude of X of t is almost equal to past sample magnitude of X of t, then step size is made to half. It's made half to that of earlier past sample step size. So like that you can observe the ADM waveform here, that is input X of t and the generated staircase waveform from the accumulator. Okay, so here if delta 1 is the present sample present staircase, if the amplitude of X of t increases, you can observe delta 2. So delta 2 is the step size of increased X of t. Okay, so then delta 2 should be higher than delta 1. So that is nothing but the logic used for ADM. So what kind of logic is used here? So whenever the present magnitude of X of t is far greater than the past sample magnitude of X of t, step size should double, and step size should be made half when we have flat amplitude variations of X of t or slow magnitude variations of X of t. Then the step size should made half. Okay, like that a logic has been implemented. Like that we have introduced a logic in adaptive delta modulation so that we can reduce the slope overload distortion and our granular noise and the granular noise. So that what we can do here, we can once by reducing the errors introduced, we can improve the SNR of linear delta modulation by making use of ADM circuit or adaptive delta modulation. Okay, let us move to the next slide. See here we can see the advantages of adaptive delta modulation. What are the advantages of adaptive delta modulation? Already we discussed it so many times. What are the advantages of adaptive delta modulation? The SNR, signal to noise ratio, is improved. Okay, or you can say that it's better than the linear delta modulation, because this ADM, because we are using logic for step size control in the transmitter and receiving section. So by varying the step size value, automatically you can reduce the slope overload distortion and granular noise. So once the errors are reduced, noise is reduced, then you can improve the SNR. Okay, so because of this variable step size, another advantage is because of this adaptive step size, the dynamic range of ADM is improved. Okay, so it's wide over linear delta modulation. Okay, so next, so third one is utilization of bandwidth is better than delta modulation. Okay, so because you are reducing the step size and you are using a logic, so utilization of bandwidth is better than delta modulation. Okay, and one more advantage is also there, as same as that of traditional delta modulation, that is here also only 1 bit per sample is transmitted, unlike in the case of PCM where we will transmit n number of bits per sample. Okay, so other than the advantages of delta modulation, that is 1 bit per sample transmission, and circuit implementation is easy, because here we don't have encoding, separate encoding process. Okay, so here in the case of delta modulation, we don't have separate encoding and decoding process. So the encoding and decoding is directly obtained, the data is directly obtained from the 1 bit quantizer section. It consists of accumulator, okay, that stores the past data in the form of staircase response. Okay, so other than delta modulation, the advantages are improvement in SNR, so large dynamic range, and utilization of bandwidth is good over delta modulation. For traditional delta modulation itself, the bandwidth is very low. Okay, so but in the case of adaptive delta modulation, we are improving SNR, and its dynamic range is more, and bandwidth is also utilization bandwidth is also better than the traditional delta modulation. So other than these three advantages over linear delta modulation, it also possesses the same advantages as that of DM, because the circuit is almost all same. Here also we are using 1 bit quantizer, so it transmits only 1 bit per sample, and here there is no encoding and decoding process. So that's why the circuit implementation is easy compared to PCM. Okay, so these are the advantages of adaptive delta modulation and the circuit of ADM transmitter and receiving section. So any doubts regarding this adaptive delta modulation? So with this module 8, you can distinguish the importance of adaptive delta modulation over traditional. Traditional is nothing but the linear delta modulation, where step size is constant. So is this module okay to everyone? Can we move to the next module? Please, one of you respond.
Yes, ma'am.
Okay, thank you. So, okay, thank you. So we can move to the last module in this unit 1. Okay, so wait for a few seconds. I will upload that module. So where we can compare, all the 4 types of pulse digital modulation techniques. So we studied PCM, and we studied the improvement in PCM. Okay, so that is by reducing the redundancy problem in traditional PCM, we introduced a differential PCM, And second type of pulse digital modulation is delta modulation. So delta modulation is specially preferred to reduce the channel bandwidth. Okay, but one thing that you should remember is that in delta modulation SNR is poor. SNR is less compared to that of PCM. But why we are opting DM? In order to reduce the channel bandwidth. Okay, but in DM we have two drawbacks: slow overload distortion and granular noise. When we have amplitude based on the amplitude variations of x of t, we have two drawbacks that exist in linear delta modulation that we will overcome using adaptive delta modulation. Now in this module 9, we can compare all the 4 types of pulse digital modulation techniques. So only specifically if you want to speak, only 2 modulation techniques we studied here. Those are PCM and delta modulation, and we calculated the SNR for PCM and SNR for delta modulation. Okay, and now in this module we can discuss the comparison of PCM and DM and the upgraded versions of PCM and DM, that is a differential PCM, and what is the upgraded version of DM? Adaptive delta modulation. Okay, now in this module we can discuss the comparison of PCM and DM systems. Okay, you can see here. Okay, so after completion of this module you should be able to distinguish the PCM and DM. I think now itself you can be able to distinguish. We can see some more factors here. Okay, so let us see first the comparison of the traditional PCM and traditional delta modulation technique. Okay, so you can call this delta modulation also as linear delta modulation. So regarding the number of bits, see, already we discussed so many times that in PCM we represented n as the number of bits transmitted per sample. What is n in the case of PCM? N is the number of bits present per sample, transmitted per sample. Okay, so in the case of PCM, the number of bits transmitted per sample can be either 4 or 8 or 16. So you can take in general. Okay, in general for so many applications, you can take n as 4, 8 or 16. Okay, but in the case of delta modulation, we know that it has 1-bit quantizer. It has already we have seen the circuits of DM and ADM circuits where 1-bit quantizer is used. So how many number of bits are there? Bits per sample are there in the case of DM? Only 1 bit. Okay, only 1 bit is transmitted per sample. That is the first difference. And the second one is the number of levels, amplitude levels. Here the number of levels depends on the number of bits. What is the relation between the number of amplitude levels and number of bits in the case of PCM? Can any one of you respond? One of the student, please tell me what is the relation between the number of amplitude levels L and the number of bits N in the case of PCM. Any one of the student respond. What is the relation between number of levels L and number of bits N, number of bits per sample? L is equal to, what is the relation between L and N, number of levels L and number of bits N?
Power n.
L is equal to, yes, very good. L is equals to 2 power n. So that is the relation in the case of PCM. Okay. Now, what about the delta modulation? Here we have no amplitude levels, amplitude variation is fixed. That is delta. Because in delta modulation we are transmitting only 1 bit per sample. Based on the corresponding data, the step size may increase with a factor of plus delta, or it may decrease with a factor of minus delta, because here we are storing it in the form of staircase waveform. That staircase waveform magnitude is either plus delta or minus delta. It is varied like either plus delta or minus delta. Okay, so here we cannot clearly say like a specific relation between L and N, but in the case of PCM, L is equal to 2 power N. Here, it is varied in accordance with the earlier staircase waveform. Okay, past staircase waveform is varied with plus delta or minus delta. Plus delta when the error is positive, and when the error is negative, it is minus delta. And once again, error depends on present sample and past sample. Already we discussed. So that's why in delta modulation, the levels are almost all fixed. Okay, and we cannot vary because we'll vary the staircase waveform as plus delta or minus delta. Now, what about the quantization error? Quantization error and distortion. Here the quantization error depends on the number of levels used. Quantization error depends on the number of levels used. Okay, but what about the quantization error? How many types of errors are there in the case of delta modulation? It is Chepalma. So what is quantization error in the case of PCM? It is delta by 2. Delta is, what is the relation between delta? How can you define delta? Delta is the step size and it is equals to 2x max by L. Already equations chadvaru kada. So quantization error is delta by 2, magnitude is delta by 2, and where delta is 2x max by L. Okay, so our quantization error in the case of PCM depends on L, the number of levels used, and it is inversely proportional to L because error is delta by 2, where delta is 2x max by L. So error is inversely proportional to L. Okay, and now what about delta modulation? Here we have two kinds of like quantization errors will arise. Those are slope overload distortion and granular noise. This is mainly due to the magnitude variation of like abrupt variation in magnitude of x of t or minute variation of x of t. Slope overload distortion and granular noise will exist. Okay, these kinds of quantization errors. Okay, now what about the bandwidth? What is the bandwidth of PCM? Bandwidth, because PCM transmits all the number of bits transmitted per each and every sample. So in each and every sample we have a number of bits. Okay, so in PCM it will transmit all the redundant data information. So that's why it needs large amount of bandwidth. Already we discussed so many times. PCM requires large amount of transmission channel bandwidth for transmitting the signal, modulated signal. But what about delta modulation? It has 1 bit quantizer where it transmits only 1 bit per sample. So obviously because n is reduced to 1, n into fs will be r. So r is reduced, signaling rate will reduce, and once the signaling rate reduces, automatically our bandwidth, which is half that of the signaling rate, will also reduce. So in the case of PCM, it needs large amount of bandwidth for signal transmission, and in delta modulation it needs less channel bandwidth, okay, to transmit the modulated signal. And now what about the feedback? In PCM, do we have any feedback section like in the transmitter or receiver? Do we have any feedback section? No, we don't have any feedback section. In PCM, transmitter section consists of only sampler followed by A to D converter, where once again A to D converter consists of sampler, quantizer and encoder. So PCM transmitter has low pass filter followed by A to D converter, and PCM receiver has decoder followed by low pass filter. Okay, but what about delta modulation? Yes, it has feedback. What is the feedback? Because we are storing the past sample information in the accumulator, it has feedback. Okay, that is a negative feedback. So one thing please remember. So even though here SNR reduces, but because of negative feedback, we have a lot of stabilization in the DM circuit. Okay, so here we have negative feedback. Please remember that. Now what about complex? Circuit is complex in the case of PCM because we have like encoding and decoding process is like complex because we need to encode source encoding and channel encoding we have to do, because after encoding we need to detect the error bits, okay, and we need to correct it. So circuit is complex in the case of PCM, but in the case of delta modulation, circuit is simple because we don't have encoding and decoding process. Okay, next, what about SNR? SNR, signal to noise ratio, in the case of PCM is very good because we know that all the bits are transmitted. So obviously SNR will improve. But what about delta modulation? Delta modulation SNR is poor because there exists two kinds of errors, namely slope overload distortion and granular noise. Here SNR is poor. And what about the areas of applications? Already we discussed the applications of PCM as like audio and video telephony, and like this kind of delta modulation is used especially in image analysis as well as speech analysis. Okay, because in image analysis, we need to, for example, if we want to store the data, so large amount of data we need to store. Okay, so we need to reduce the bandwidth there, but SNR is not at all the issue. Okay, so by reducing the slope overload distortion and granular noise by making use of adaptive delta modulation, obviously this kind of delta modulation is suitable for this kind of image analysis and speech analysis. Okay, where bandwidth plays a key role instead of SNR. So even you can improve the SNR by using adaptive delta modulation. Okay, see, these are the wide varieties of applications used. Now this is about the comparison of PCM and DM, and let us go through the noise analysis. Okay, so this is SNR comparison. So already we derived the SNR of delta modulation and SNR of PCM, and we considered the input signal x of t as AM sine 2 pi FMT. Okay, for that input signal, the signal power is AM square by 2R. Okay, and if we normalize the signal, then it will be AM square by 2. Already we defined all these things, and we got the SNR for delta modulation as 3 by 8 pi square FM square TS square, where FM is the maximum frequency of message signal, TS is a sampling interval. Now, divide the numerator and denominator with pi. So multiply the numerator and denominator with pi, so that in the denominator you will get 2 pi FM whole cube. Okay, so the 2 pi FM you can write it as angular frequency omega m cube, and 3 pi Fs cube by omega m cube. That is the SNR for delta modulation. See, we derived this in the last class only. Okay, and what is the quantization noise power in the case of delta modulation? N is delta square by 3. Now, what about the same for PCM? For PCM, it is related to L, where L is the number of amplitude levels, which you can further replace it as 2 power n. What is the relation between L and n? L is 2 power n. So what is the expression? How much you got? 3p L square by x square max. For normalized input, x max is 1 and p is equal to am square by 2. Please replace p as am square by 2. So you can get 3 am square L square by 2. This is the SNR for PCM. If you observe the SNR for DM and SNR for PCM, SNR for DM is proportional to Fs. What is Fs? Sampling frequency or sampling rate. Okay, and how the SNR of PCM, SNR for PCM is related to L, is proportional to L square, where L is 2 power n. And what about the quantization noise powers? Quantization noise power in the case of delta modulation is delta square by 3, and in the case of PCM it is delta square by 12. So like this you can write so many comparisons, and even if you can go through the block diagram, and in the case of DM you have 1-bit quantizer, and in PCM we have traditional traditional quantizer, and inka chapali ante like in the case of DM you can say that encoding and decoding principles are there. Sorry, in case of PCM we have encoding and decoding process is there, and in DM we have a circuit is simple, so we don't have like encoding and decoding separate process. here we have accumulator. Like that you can write so many differences. Okay, this is about the SNR comparison. And regarding noise power, quantization noise power is delta square by 3 and quantization noise power is delta square by 12. And we have derived this SNR for DM and SNR for PCM in the respective modules. Okay, now I want to give you one problem. So what is the improvement in SNR DM of DM when sampling rate Fs is doubled? So we can solve this problem by using this equation. Already we know SNR for DM is like 3 pi Fs cube by omega m cube. Okay, like this is one question given in GATE. Okay, so like olden days it has given. So what is the improvement in SNR for DM technique when Fs is doubled? When Fs is doubled, please observe the equation. SNR is proportional to Fs cube because 3 pi is a constant and omega m is also a constant because maximum frequency of message signal is always a constant. Okay, maximum frequency is always constant. Okay, so SNR is proportional to Fs cube. So what can be the change in SNR? Let initially the initial SNR be SNR1 and once the sampling rate Fs is doubled, let us take the SNR as SNR2, suffix 2. So what can be the improvement in SNR? 2 Fs whole cube divided by Fs cube because SNR is only proportional to Fs cube. And regarding other things, it is constant. So we can say that it is 10 log 8. So 10 log 8 value is 9 dB. So what is the improvement in SNR for delta modulation in dB when sampling rate is doubled? When sampling rate is doubled, so Fs becomes 2 Fs whole cube. Fs cube becomes 2 Fs whole cube. So 2 cube will be 8. So Fs cube gets cancelled. So you will get log 8 multiplied by 10. So you will get it as 9 decibels approximately. So when Fs is doubled, SNR will increase by a factor of 9 dB. Okay, so now let us move to the next slide. You can see SNR for PCM. So what is the SNR equation in dB for PCM? So if you take the normalized power P as less than or equal to 1, we calculated it as 4.8 plus 6n. It is less than or equal to 4.8 plus 6n. See, always remember this dB equation, SNR dB equation for PCM, and everywhere this factor behind the 6n will change based on the amplitude of message signal or based on the signal power. The constant value will change. Sometimes it will be 4.8, sometimes it is 1.76 if AM is 1 volt. Like that, the constant value will change. The value beside the 6n will change, but always this 6n remains constant. It is 6.02 something. Okay, so that's why this PCM dB equation is called as 6 dB rule of PCM. What is 6 dB rule of PCM? Based on the, for example, if you are increasing 1 bit, each additional bit of quantization level increases the SNR by 6 decibels. For example, if n is equal to 1, the SNR will be 4.8 plus 6. If, for example, n changes to 2, you are increasing the n value by 1. So each additional bit, so 6 into 2, so it will be 12. So 12 plus 4.8. So when compared to the past value, we see SNR increases by a factor of 6 decibels. So each additional bit of quantization level increases the SNR by 6 decibel. So that's why this above equation is generally called as 6 dB rule of PCM. So SNR equation of PCM in decibels is generally called as 6 dB rule of PCM. Okay, because each additional bit of quantization level increases the SNR by 6 decibels. Okay, this is about the SNR of PCM. Now this is a comparison of PCM delta modulation, adaptive delta modulation, differential PCM in all aspects. Okay, So we discussed it so many times. First one is number of bits, second is number of levels, third is quantization error. So this slope overload distortion and granular noise we can avoid by using adaptive delta modulation. Okay, and when compared to the bandwidth, so coming to the bandwidth, highest bandwidth requirement in PCM and the lowest bandwidth is in adaptive delta modulation. And when regarding SNR, we have highest SNR in PCM and lowest SNR. Okay, so we have low SNR in DM. Okay, so lowest SNR in DM, and you can improve the SNR of DM by making use of adaptive delta modulation. So in all the techniques, feedback is required except in PCM. Except in PCM, because in DPCM also we have feedback section, we have prediction filter. Okay, so except in PCM, feedback is necessary for all the networks, and system is complex in PCM, and all other system is simple, and in ADM it is still simple, ADM and DM compared to DPCM, and system is highly complex in PCM. And area of applications, already we said you, audio and video telephony for PCM, and speech and image analysis for like delta and adaptive delta modulation. Okay, so this is all about the comparison of the two main techniques, PCM and delta modulation. Okay, so these are the two types of pulse digital modulation techniques. With this, we can conclude the first chapter. Okay, so by this module, you can compare PCM and DM in all aspects. Okay, and coming to the course outcome of Unit 1 is you can be able to distinguish the two kinds of pulse digital modulation techniques, namely the PCM and DM in all aspects, and along with that we can be able to compare using SNR also. Okay, so with this almost we completed the Unit 1. Okay, so in the next class we can continue with Chapter 2 or Unit 2, where we can study the digital modulation techniques for all the corresponding techniques like amplitude shift keying, frequency shift keying, and phase shift keying. Almost all our input is digital in nature, unlike in the case of pulse digital modulation techniques where input is analog, and here you have converted analog into digital. Okay, but in the case of digital modulation technique, we'll take directly the input as digital signal. So those are of three types. Already we discussed somehow: amplitude shift keying, frequency shift keying, and phase shift keying. Okay, we can go through Chapter 2 from next class onwards. Okay, with this we can conclude the Chapter 1. So any doubts? So please wait for 2 minutes. I will take the attendance, so then you can leave. So today, now itself, I will post all the modules. Okay, sorry for the delay. I will post now itself, so that we don't require any kind of modification. Okay, so now I will post the whole Unit 1. Okay, from next class onwards, we can start the Chapter 2 or Unit 2. Okay, so in that we can discuss three kinds of modulation techniques, namely amplitude shift keying, frequency shift keying, and phase shift keying. Okay, so any doubts in the Chapter 1 other than the so any doubts, or else we can wind up the session.